Welcome, everybody, to the 24th Hintze Lecture. My name's Roger Davies. I'm the director of the Hintze Centre for Astrophysical Surveys. And it's my pleasure to introduce tonight's speaker. First of all, I want to let you know that the lecture has about 300 people signed up online, so we probably have quite a few people watching online. And at the end of the lecture, we've got moderators here looking for questions for online, so people in the hall will get to ask questions, but also we'll take questions from those online. So I'm particularly delighted today that we're joined by the newly ennobled Baron Hintze and the Lady Hintze, whose charitable foundation makes these lectures possible. So we're immensely grateful, as always, to Michael and Dorothy for being here. And it's my great pleasure and honor to introduce Dr. Matt Mountain to deliver tonight's lecture on the James Webb Space Telescope. Matt is the James Webb Space Telescope scientist, 2 telescopes there, and has been centrally involved in the project for over 20 years. Matt's an infrared astronomer. His research interests are in star formation and advanced instrumentation. Over 4 decades, he's been central to a number of innovative telescope and instrument projects. After his degrees at Imperial College, he moved to the Royal Observatory, Edinburgh, where he led a team that built a new spectrometer for ushered, the 3.8-meter telescope on Mauna Kea. At the time, that was a very big telescope. After that, in 1992, he was appointed first the project scientist for the Gemini project, and 2 years later, he became the project director. That project was to build 2 8-meter telescopes. So they've gone up by a factor of 2 now, 1 in Hawaii and 1 in Chile. And the partnership was a 7-nation partnership, including the UK. The UK office was here in Oxford, and several people here played a key role in that project. Matt took that project from a construction project to a fully operational 2-telescope observatory over about 10 years. In 2005, he was appointed to the directorship of the Space Telescope Science Institute that runs the Hubble Space Telescope Science Program and is now the operations center for James Webb. He led that institute for an exciting decade, which included the dramatic last servicing mission in 2009 and 2 big scientific survey initiatives, the Multi-Cycle Treasury Program and the Frontier Fields Program. In 2015, he was appointed to his current position, that is the president of AURA. And AURA is the Association of Universities for Research in Astronomy, and it runs the Hubble Space Telescope, the James Webb Space Telescope, the Gemini Observatories, the US National Observatories, the Vera Rubin Observatory, and the US Solar Observatory. So much that is central to modern observational astronomy. So who better to deliver the 24th Hintze Lecture, the James Webb Space Telescope, creating a new era in astronomy? Matt.
Thank you, Roger. Thank you. Well, it's a pleasure to be here to talk about this new era. But I actually want to start this lecture on Christmas Day last year.
One minute.
Thumbs up from Jean-Luc Voyer. All systems are go. We're inside a minute now. T-minus 30 seconds and counting.
Moving out to the observation platform that is right next to the Jupiter control.
She wasn't the only one. Hyperventilating.
Unité. Top.
And we have engine start. And liftoff.
Décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Fantastic pictures of this telescope.
Go Webb, go Webb.
Yes, go Webb.
Ironically enough, as we marvel on this view from the upper stage camera, this will be humanity's last view of the James Webb Space Telescope.
So that transition from French to English or American was the point at which it became our problem. And this is the story of the James Webb, told in several chapters, ups and downs, and the launch, believe it or not, was not the most stressful period. And there were other periods ahead of us, in fact, before us and ahead of us, which I'm going to touch on. Now, this story starts, of course, 400 years ago, with the belief that if you have a small handheld device, whether it be a microscope on the left or a telescope on the right, you can change the world by making an observation. And of course, famously, Galileo lifted his telescope to the sky here and showed the Dodge of Venice, seeing the moons going around Jupiter and realizing that the church was wrong, that Copernicus was right, and in fact, the sun, not the earth, was the center of our solar system. That began those irrevocable changes that observations make possible. And that's what modern science has done. And today, perhaps one of the most powerful telescopes, up until Christmas, or at least a bit further on, was this telescope. Certainly the most productive, produced more papers than any other space mission. The first time we put a major telescope, optical telescope, above the atmosphere to give us a very clear view of the space. This telescope travels at 17,000 miles an hour, roughly 300 miles above our head. And of course, what it does is take pictures. And that's what I also like to remind people. It takes pictures in actual optical light through various filters, combines them, takes them down, and creates an actual picture. That if you could, your eyes were the size of a Hubble, roughly 2 meters, and you could keep them open in a vacuum for roughly a week, this is what you would see. This isn't what we're doing with the James Webb Space Telescope. The start of the James Webb actually started before Hubble was launched. The director at the time says, look, we're getting ready for the Hubble. What are we going to do next? It takes a while to do these missions. And so he called a group of astronomers to Baltimore at the Space Telescope Science Institute to discuss what would the next generation space telescope be. And one of those people was your very own Roger Davis here, which I didn't know at the time until I looked back and saw your name there, Roger. So thank you. And the decision was that this should be an infrared telescope. The infrared looks at heat, not light. Infrared looks through dust clouds, as you can see looking through this plastic bag. It shows us a different view of the universe than you see in optical light. And in fact, the image there, the image as you see here, shows a different image of what the Webb sees when you look at galaxies. You look through the dust, you actually see where stars are being made and being formed. But that wasn't the only reason we actually went to the infrared. The Hubble, the director at the time, decided to stare at a single blank piece of sky with the Hubble, no bigger than a drinking straw, and stare for 10 days. It was a very controversial decision. People pushed back, but it was his time. And so for 10 days, we stared at this, not we, but the collective we, stared at this single blank point. And in that soda straw were 3,000 galaxies. You can imagine multiplying that across the sky and how many galaxies there actually were. That was the first time we got a sense of scale and the quantity of galaxies out there. The other thing that we noticed is, of course, as you look deeper into these images, you're looking back in time. Light is finite. And you can actually fly through this field, and you begin to see the galaxies deeper, further back in time, a little bit more disheveled. They're a little stranger shape. It takes light time to travel, so the deeper you look, the further back in time you're looking. And as you look deeper and deeper and further back in time, we see less and less galaxies. In fact, they get very sparse. And we see just a few galaxies that only appear to be red or orange. And you see all this space. And here, in fact, is one of the most distant galaxies at the time. The nice was, because James Webb just does beat that. What are we seeing? Have we run out of galaxies? Well, of course, the reason is no, because as the universe expands from the Big Bang, it stretches time and space. And actually, the most distant galaxies, the further back in time, the light gets shifted into the infrared outside of the range that the Hubble can see. And there was a realization that we weren't seeing the first galaxies. To see the first galaxies, we'd have to go to the infrared wavelengths. And that was the scientific motivation for the James Webb. So Hubble looks at optical wavelengths, as I show you here. To see this faint galaxy, a new group was put together that NASA began to read. Aura brought this group together based on that first workshop. And look, on the front cover is the Hubble Deep Field, led by astronomer Alan Dressler. And the first thing we realized, or they realized, is that to see these very first galaxies, we're going to need a bigger telescope because these galaxies were faint. In addition, we had to move it to the infrared. And that's where the concept of the James Webb Space Telescope was born, to look at a big infrared telescope to see the very first galaxies. And that was the motivation. However, in the intervening years, a number of science cases emerged that also need a big infrared telescope. And I thought I would touch on some of these, because some mysteries are beginning to emerge in this darkness that we were unaware of when the Webb was first brought to pass. So here is our picture of the universe. The Big Bang imprinted fluctuations on the microwave background. Then there were these dark ages when we don't know what happened. There is no data. That's what the James Webb was supposed to look at. Galaxies formed, the universe expanded, dark energy took over, accelerated the universe, and this is our picture. However, some inconsistencies in the last 15 years are beginning to emerge in this picture of our universe. From observations from other space telescopes, for example, Planck looking at the microwave background, additions to measurements from Gaia, European spacecraft that looks at very precise missions, it gives us distances. There's a dichotomy beginning to emerge, which is interesting and makes the Webb uniquely useful. So, I'm going to show one graph after this, one of two graphs in this entire talk, but I think this is an interesting problem. The expansion rate of the universe as we observe it today is defined by the Hubble constant, a number. And that's what we see. We take the early physics that we've understand from that first moment, 400,000 years after the Big Bang. We put everything we know about physics, we crank the handle and make predictions of how fast the universe is expanding. And if they agree, our model of the universe is secure. And that was the time, in fact, when Hubble first measured the Hubble constant to a precision about 10%. On this graph here, you will see Hubble constant on the y-axis, going fast at the top, slow at the bottom. Along the x-axis is the year of observation. So when Hubble made the first measurement, there was good agreement between what we saw in the microwave background and what Hubble was measuring. Then Adam Rees and his team and Brian Schmidt, who's I believe spoken here too, and Paul Solomon began to make more precise measurements of the early redshift, and it wasn't agreeing so well. And they needed dark energy to actually make the agreement, and because of that discovery, these three got their Nobel Prize. Since then, things have got a little more complicated, because the recent measurements with the Planck and the increased precise measurements with Hubble are beginning to disagree, and disagree quite profoundly by, in fact, 5 sigma, that magic number in physics that tells you, okay, this is not a statistical fluctuation, this is something real. So you can see these two ways of predicting the Hubble constant from the early universe, from the Planck, or from Hubble are beginning to disagree. Something is missing in our calculations of the universe. There's something wrong with gravity, there is a new force, or something happened that we don't understand. The two proponents of these two views, of course, are given by Adam Rees and George Eustathio, who was on the Hubble, and Adam on the Hubble and George on Planck. And George Eustathio calls this a crisis. Adam Rees calls it a problem with the physics. Now, it's actually not really between them, it's really between these missions. The question is, what is going on? Is it going on in that place where we have no data? It turns out that already James Webb is making a difference, because here are some very recent measurements from 2 weeks ago, measuring the actual precision of Cepheid variables. We can also already know, because of the infrared, James Webb is going to help this at least even more precise measurements. We have no insight yet if we can see anything in those dark areas. But that's also, it turns out, was a prescient decision to want a big red telescope. Here is another one. What we didn't know 20 years ago is that there are planets everywhere. If I'd stood here 20 years ago, we wouldn't know that when you look up at the night sky, almost every star you see has a planetary system. We didn't know that 20 years ago. Today we do, because of the statistical measurements we have made with the Kepler satellite that found thousands of satellites, and they only pick up if the star goes in front, and so you work out the orientation. Now we know there are planetary systems everywhere. It turns out that if we want to ask what's on these planets, we also know statistically that at least between 10 and 20% of Earth-like, of solar-type stars like our sun, have Earth-like planets in this habitable zone. That is, the not too cold or not too hot zones that allow liquid water to be there. So the question is, can we find any of those? It turns out the infrared is a good place to go look, because if you take some spectra of 3 well-known planets in our solar system, split the light up into its component parts, what we call a spectrum, at the infrared you see this. The top spectrum is of Venus, the bottom spectrum is of Mars, and the middle spectrum of that just right zone is Earth. And look at the difference between the two. It turns out what we need to understand do we have an Earth-like planet is a very large infrared telescope, which is just as well we were building one. But that was luck, fortuitous. So now, in fact, exoplanets has become a central part of the James Webb Space Telescope, and why so much work has gone in to create these two missions, to create this mission. And look at the comparative size. Okay, we're going to build a 6.5-meter telescope and put it into space. How hard can that be? Turns out to being quite hard. I always put this up for my scientific friends to remind them, this is not an original quote, this comes from CERN, that without engineering, physics, science is just philosophy, or physics is just philosophy. A huge engineering team had to be assembled to actually put this together, because the engineering challenges were quite profound. Here is the Gemini telescope that Roger just told us about. You know, it was advanced in its day. One of the largest infrared mirrors, fully infrared optimized, but it was rather heavy. The mirror weighed 22 tons. The structure itself weighed roughly 380 metric tons, if I've done the conversions right. To fly this thing, we had to do rather better. We had to reduce the mass of the mirror by a factor of 60 and the mass of the structure by a factor of 60. Oh, we had to do one extra thing. Because it's an infrared telescope in space and we don't want the background of the telescope to dominate, we're looking for very faint signals. The telescope must be cooled. Gemini sits traditionally in Hawaii, believe it or not, at roughly 0 degrees centigrade. To make this telescope work, we had to cool the whole telescope down to minus 230 degrees centigrade, or 30 Kelvin. And if that wasn't enough, we had to pack it in a rocket and then unfold it 1 million miles from Earth and hope that it worked. And this is what we had to do. Here you see an animation. The sunshade that you're seeing there unfolding protects the telescope from the sun and the Earth and allows it to cool to interstellar space. It is 5 layers of space blanket, the size of a tennis court. And as we will talk, it turned out to be a harder problem than we realized. The mirrors themselves started in a mine in Utah.
How tough is it to find beryllium?
It took us about 30 years to gather all the data and information to design and develop this mine.
And once the ore leaves this mine, is it ready for the folks at the James Webb Space Telescope program to use it to build the mirrors?
No, after the ore material leaves the mine, it is shipped to the processing plant about 50 miles east of here.
What it turns out, that to make mirrors work at minus 230 degrees centigrade, and they have to be perfect, is you have to make a mirror, polish it perfectly warm, cool it down, and it distorts. You have to measure the distortions to less than the wavelength of light, and then polish in the reverse distortions. So when you cool it the second time, it bends precisely into the right shape. When I first heard about this, I said, are you crazy? Yes and no. Here is the test chamber. There's only one chamber in the United States that was big enough at the time and cold enough to test these mirrors at the Marshall Space Flight Center, hence all the journeys. The measurements had to be done somewhere else. The machining had to be done somewhere else. But what we discovered that if you use beryllium, which is a metal, and we did this, we could actually polish this to the precision required. And to get a sense of how precise it was, if you took one of those mirrors and stretched it across the continental United States, I apologize for using that country at the moment, no bump had to be bigger than 2 inches or roughly a centimeter. So that was the first challenge. Second problem was, because we're unfolding this telescope out in space, we had to be able to adjust it. That means we had to take mirror segments about this size that weigh roughly 20 kilograms and move them by nanometers. Now, a nanometer is a fractions of a wavelength of light. They're roughly 100,000 nanometers in a hair, 600 nanometers in the kind of light you see. The engineering challenge was to make mechanisms that could move these mirrors in 10 nanometer steps in a vacuum at minus 200 degrees, a million miles from Earth. We decided we better test that before we tried it. It turns out there was no chambers big enough in the United States to test it, except this old chamber that was used to test the Apollo capsules. It was called Chamber 8. It's actually a national asset, and we had to get permission to convert it. It was owned by NASA, so I wasn't quite sure why we had to get permission, but it was theirs. And we had to build the entire telescope, cool the whole volume down, and put the telescope in. That shows you the scale that is changing with science. Our telescopes now are more complex and larger than the manned program Apollo missions. And so we got the whole telescope assembled to test it out. And what did we learn? Things go wrong. The first thing that went wrong was, just after we got the whole chamber in there, we had poured liquid nitrogen, we got liquid hydrogen, liquid helium going, all the team were down there, a hurricane turned up. Now, we were spending at this point roughly $1 million a day, because there were so many people on this project in various parts of it. The team decided to camp and stay down. And through the hurricane, well, we got 51 inches of rain, the roof started leaking, and so this is the guys operating in their tents, carried on operating through the hurricane. Remember, this is a massive chamber. We weren't worried about being blown down. We were worried about water, food, power. Power remained on. Food turned out to be a problem. And so in the end, Northrop Grumman and Ball Aerospace flew food down and people down. We finally got some liquid nitrogen about 3 days later. And then the excess food, the actual JWST team actually helped out with the community for another week. We actually got through the hurricane and tested, and all of those optics that we talked about worked. Except, of course, this is being done in gravity, 1G. The gravitational sag of a beryllium mirror is enough to distort it. So we had to calculate how much distortion and assume that we knew how to correct it back, and I'll come back to that. We then had to assemble and put the whole thing together with the sunshade. Here's the sunshade, finally got that working at Northrop Grumman. Again, it's the thickness of a space blanket, it's 5 layers, and it has to expand automatically under control and not rip. Turned out to be not easy, but here it is. And we finally, what did we learn? Things can go even worse. We finally got the whole telescope assembled. When you launch a spacecraft, however delicate the optics is, it gets shaken by the rocket. And so you have to make sure the whole thing doesn't shake to pieces. So you take your careful telescope and you put it in a massive shake room and you start shaking all that optics. And all of us sit and watch this in horror as we basically subject the whole spacecraft to the sound and thermal and kinetic vibrations of a rocket launch. And when they did that, something happened.
We found a screw and a nut. We had a few dozen that actually separated in this test, because there's 1,000 of these little screws. No, there's probably a lot of people on high floors of buildings waiting to hear that Webb has made it today. We're kind of one of the, say, more humbling points in the career when you know you have to go tell people that test wasn't successful.
These 10 nuts, can you see them? These 10 delayed the project by 800 days. And you might say, how do you know it's 800 days, Matt? Well, we were burning $1 million a day, and Northrop Grumman had lost all its credibility with Congress, and NASA had lost all its credibility with Congress, and they said, Matt, we need you to do something. We need you to go and ask for an extra $800 million. At which point, a staffer who I know threw a glass at me. However, it did result, we needed to have a hearing to get through to find out if things going. So here was day one of the hearing in front of the science committee.
And when you talk about, the real difficulty of the mission, you have to come to the point with this type of mission, you end up with, you have to, every screw has to have its quality tested, and that's part of this. Well, I can tell you, this is about the biggest screw job I've ever seen, and it's the taxpayers getting screwed here.
It was a tough few days. The NASA administrator was there, the Northrop Grumman CEO was there, everybody was there, interrogated for 2 days. Plans were shown of what we're going to do next. The next day, this is the next day.
And welcome to the second day of the hearing entitled James Webb Space Telescope Program Breach and Its Implications.
We've had a lot of discussion about cost, and the cost matters. But I will tell you, taxpayers and all of us are way more concerned about value than cost at the end of the day.
James Webb should continue based on its extraordinary scientific potential and critical role in maintaining U.S. leadership in astronomy and astrophysics. Let's finish this incredibly important project.
Inspiring and challenging projects such as the James Webb Space Telescope are an investment in our future.
Now, this is what they don't teach you at graduate school when they say, do you want to build telescopes for the US federal government, that you end up doing things like this. I will tell you what happened. A senator who actually was very responsible for providing the money came up to me, pointed a finger in a chest and said, wherever you do, expletive ever again. But we got through it. Management was changed at Northrop. Things were changed at NASA. A new director came in. And by January of 21, we had the fully assembled telescope. And we were able to wrap it up and get it down to Kourou to launch. But those of us who worked on this know we had to get through the launch, but then we had to actually work out if any of this worked. Could we unfold it? Could we line up the optics? And so on the 25th, we actually launched it, as that launch just shown, and then began a slow process of unfolding. And to our utter amazement, everything worked. Every day we went in, and every day we ticked another box. 300 single point failures, one by one. The system engineer kept ticking them off, saying, I can't believe there's another one. Here is the final day of deployment.
This is Step Lead on Ops. We have reached the end of deployment, and we are preloading into the latch pad.
Okay, copies.
And we have a fully deployed JWST observatory.
The guy they're looking at is the guy who designed the deployment system. So now we have a deployed telescope. What we have is a deployed spacecraft. We don't actually have a telescope yet. So when we move out to L2, we had to actually try to make it into a telescope. We now have a fully deployed sunshade, the telescope is all out, but the mirrors are just randomly placed within some tolerance. And we had to start searching for the very first star. And after doing a raster scan, we found one star that hit one mirror, that hit one camera, so we at least knew that one of the mirrors worked. That allowed us to refocus the camera to look at the mirror itself. So this is actually a picture of the James Webb mirror 1 million miles away, all of them. So now we knew we had all our segments, and at least one mirror was pointing in the right direction. That allowed us to find all the other mirrors. And then we had to work out, do the mirrors actually work? So each one of these mirrors can be rotated, tilted, and bent. And any of you with optical knowledge, you will know that a lot of aberrations were inherent in these mirrors, and the problem was we'd only tested them in 1G. We did not know whether they were going to work in 0G. And so we began the process of measuring and tweaking the mirrors, literally nanometers at the time, changing the surface. And here's the set of iterations over the course of 3 weeks. At the end of this, we had diffraction-limited segments. We got those calculations right too. We then had to actually make them all point in the same place. We still have only 18 mirrors. We don't have a single telescope yet because the distance between the mirrors, what photons can still see. Now we had to do wavefront sensing, which now we have to move the mirror edges within the fractions of wavelength of light to 10-meter precision. But first, we just made sure we had all the mirrors aligned. There is the first picture. And then we had to make the movements, basically change the way we were thinking by 1 million. We had been moving the mirrors by millimeters to line them up. Now we had to move them by nanometers. And this is the first diffraction-limited image that we saw when we did that. Most interesting, when this image came down, nobody was actually looking at the image. They were wondering, what's all that stuff in the background? Look at all that. They're galaxies. The noise in this image is galaxies. There are galaxies everywhere in this image. And that was the first realization, this telescope really works. Because this was a 30-minute exposure and there were just galaxies. That was the background. There was no empty sky. And so that began the era. And later on, we began the first science images, and the excitement that created, which I can answer questions about why that was across the globe. Everywhere we had parties, and it was across every site. We had 2,000 events across the globe for the first release. The newspapers across the world also celebrated. We were quite amazed by the interest the James Webb created. In fact, it made the Hubble guys quite jealous, I will tell you. And I will come back to that. But of course, the science is what we're really here to see. But the very fact it worked generated a kind of interest which I think even NASA underestimated what an impact focusing on this mission NASA, ESA, and the Canadian agency had actually created. 20,000 people working for 20 years on this project, and this is the kind of coverage they got. Even Times Square, and as a friend of mine said, as you'll see in a minute, how many times does Times Square show a spectrum? And if you watch, in a minute, up will come a spectrum. Now, the images that you're going to see are not optical images. That's the most important point. They're infrared images that we are basically going to translate into the optical so you can see them. So we take images, of course, as it says here, through various infrared wavelengths, then map them on to different colors. So here is your first peak. This is the Carina Nebula. It was on the front page of the New York Times. And here, it's a massive region. But it's an infrared image, not an optical image. What you do is you take them up, you take them through their various colors. We translate those colors. In fact, there was actually quite a few colors in here. And then we map them onto optical colors so you see them. So what you're looking at are infrared images moved to the optical so you can actually see them. And we keep track of exactly how that translation is done. There's a certain integrity here to doing this. So let's see how far we got. Here's the first result. This was looking at a single point in the sky, no bigger than a grain of sand held by your hand, staring for roughly 2 hours. And here's the first deep field, at most 4 or 5 hours, if I remember correctly. And this is the deep field. Wherever you see is galaxies. There's very little empty sky. And if you zoom in, you see there's some very red galaxies. Look at that little splodge coming up there. Turns out that galaxy is from 13.1 billion years ago. 0.7 years after the Big Bang. It turns out Webb is sufficiently powerful. We can take the light and, of course, break it up into individual components using one of the spectrographs, which is what we show you here. And those who are used to seeing galaxies say, okay, yeah, I can see lines. I see hydrogen, oxygen, and neon in this galaxy from 30.1 billion years ago. The point is, you're seeing the first oxygen and the first neon ever created in the history of the universe. This is the first generation of those elements in this galaxy. And it turned out to be easy, which is remarkable. And in fact, we can do this in multiple places with these instruments and actually look at the redshift to get the whole three-dimensional picture of these galaxies. And if you look even more closely, in great distance, wherever you look, you see different galaxies of different types. There is no empty sky with the James Webb, which blew our minds at some level emotionally. Of course, we'd all done the calculations, but none of us had internalized what we were going to see. This data also created a great slew of papers. Here is one of them. Panic. There are too many disks. Here, for those of you who are used to seeing this redshift along the bottom, the fraction of various, whether it's a spheroid or a disk or a peculiar galaxy, compared to Hubble, and you can see the downturn and then the upturn of the Webb data shows, oh my goodness, there's many more disks there than there should be from our models. We don't know if this is correct, and as a colleague of mine said quite cynically, maybe astronomers need to get more used to seeing high redshift galaxies in the optical rather than the ultraviolet. So we don't know yet, but it already is generating results like this. Or you can look at this. Here's the Cartwheel galaxy taken in the near-infrared. It's a well-known galaxy. These two galaxies at the top have created this sort of broken this galaxy apart. You see the starlight. We see lots of darkness. Just look at those two areas here. Look at the difference in these two galaxies on the left here. Go to the far infrared, mid-infrared here, the thermal infrared, and it gets filled in by dust. That's where stars are being formed from the gravitational interactions in there. Look at the two galaxies of them. One of those galaxies is forming lots of stars. The other one is forming none. Why is that? They're the same age. They come from the same collision. What's going on here? If we move to the very far infrared, where we're seeing the dust itself, we see the bright nucleus, because there's a black hole there heating up the dust. So we know there's a black hole in the center of this one. Actually, it turns out there's a black hole in the center of that lower one, which is suppressing the star formation. So we're beginning to see the evolution of star formation and with black holes and the relationship between the two, because the top galaxy is actually forming stars, as you can see. And this was just an engineering image. Stephen's quintet, and as Roger points out, there's one missing. Yes, it's actually only 4 galaxies here. I can't count the ones off the side. These are 4 galaxies. The one on the right, you can see on the left, you can see the individual stars. That's because it's only 40 light years away. It's just coincidence. You can see the individual stars in the infrared. The other 2 galaxies are dancing around. The first thing you notice that every image we take is a Hubble deep field. Look at the background. The other thing is quite interesting. This is what's going to happen to us when Andromeda comes our way in roughly 4 billion years. It's heading towards us, and this is what will begin to rip our own galaxy apart. Look at the collision place in between. Now we move to the infrared. There we can see stars forming with the tidal tails actually causing the compression. If we go to the even further infrared, we can look through the dust and see where those stars are being made. And we can begin to see the nuclei really coming to life. Look at the one at the top. The very bright thing with that cross is because it's so bright, it's actually creating diffraction in the telescope itself. That is a black hole heating up the torus. Look how clear it is. And just in case we didn't know, we have a spectrograph which can actually take a 3D image of this. It's called the integral field spectrograph, and it can look at the flowing gas. So we can measure the velocity fields and see the jets. You can see down the bottom here, there's towards us and away from us, and the argon lines, the neon ions, and the hydrogen. That tells us we're seeing a jet. This technique of integral field spectroscopy is the first time we've flown this in space. And just remember, the reason we did that is because here at Oxford, you developed this technique. So Roger, your technique is now flying on 2 of our instruments. We can look a bit closer to home. This is the Tarantula Nebulae in the Large Magellanic Cloud. You say, why is that interesting? Well, this galaxy actually has very low metallicity, i.e. has not formed many generations of stars. It's sort of like a prehistoric precursor of ours. We begin to ask, well, what's happening in this region of star formation inside this galaxy of very low metallicity? Well, first of all, we can see stars beginning to eat away. That red-orange on the outside is molecular hydrogen being shocked. If we zoom in, you can see the stars here and the molecular hydrogen here, and these are not visible at wavelengths. We can be seeing the stars begin to interact with its molecular cloud. If I go to the thermal infrared, we begin to see just the dust, and this gray are these strange polychromatic, polycyclic aromatic hydrocarbons, imaged here, creating elements that have been created in stars, being regenerated and put back into the interstellar medium for the next generation of stars, even in these low metallicity galaxies, beginning to get a handle. It's like doing archaeology of our own galaxy, looking back in time when the metals were far less than ourselves. Then there's the Eagle Nebulae. The only reason I show this is because it's pretty. But there's another lesson here. If you look in the infrared, which of course is the one on the right here, you see all those stars? Those aren't galaxies this time. You don't see them in the optical image because the dust and the gas is obscuring the fact we're actually looking through the bulge of our own galaxy. So these are the stars from the rest of our galaxy, which you can see now quite clearly in the infrared. And if you zoom in, which we do here, at the very tips, you'll see the bright little modules of young stars coming out of their cocoons for the first time. If we zoom in, you can see it a little bit more carefully. Those little red bright dots right at the end are young stars coming out of this cocoon of dust. There's an ultraviolet field eating this dust away, creating shocks, collapsing, creating star systems. And some of these other red things are jets because disks are forming. The only way to lose angular momentum when a disk forms is to make a jet, like the ice skaters spinning on the ice. But if you move this to the far infrared, where you can actually see the dust. Where is the dust? It's vanished in this picture, but what James Webb can do is go to a wavelength where the dust itself emits, and we can see what is the substructure of dust that is actually doing this star formation. This was released on Halloween in the United States because it looked like the Dementors. But this is an image of the dust in the nebulae. And there's so much detail here. You can go in and look at individual jet structures and so forth. And the bright stars are right at the tips there, are young stars being created in planetary systems. We can look at stars at the end of the sequence of life. This is a star similar to our sun. It's called a planetary nebulae. It has thrown off, it has run out of hydrogen, it has thrown off the outer layers. The elements have been thrown into the interstellar medium. This bright white dwarf is shining, eating away the cavity, as you see here in the short waves, and then there's dust and elements that are created outside. If you look up at the top corner here, it actually happens to be a galaxy just interloping. And if we go to the thermal infrared, that dust disappears in that galaxy, but also you're seeing the back of this nebulae for the first time. There are dust grains being created from this grain. So here's another image. A colleague of mine got this image taken, Heidi Hamel. She loves Neptune and ice giants. It was a picture that was taken of Neptune by James Webb, part of a science program which she released for us. For the very first time, because of the resolution and its sensitivity to low surface brightness phenomena, we can see the rings of Neptune, which I confessed I didn't know they had until I saw this. And I was reminded, well, Voyager saw them in 1999. Oh, sorry, Heidi, yes, I forgot about that. But that's the point. This was easy. But that's not the point of this figure from my perspective, because if you zoom out, look at that dynamic range. We have a planet in our own solar system, a star in our galaxy, and then background galaxies in a single exposure. That range of phenomena is what the James Webb has created. So where's this story taking us? First of all, I love this quote. Dennis Overby, unless you live in the United States, you probably don't know, he's a well-known science writer for the New York Times. He was always very skeptical about James Webb. He always said, you're not going to produce pictures as good as Hubble, Matt. Hubble's so iconic, what are you going to do? Well, he wrote this article because of the resolution that it gave us, and it was this image that changed his mind. It's an image of Jupiter, very easy to do. You can see aurora in the top and the bottom, and the different layers of structures because you're looking at different depths because you're looking at the infrared. This tells us that planets are actually infrared objects, which of course brings us to, okay, what about that experiment? Can we do that experiment to find out if in the atmosphere of exoplanets, that means planets going around other stars, what can we see? Well, this is a hard problem, so we started by a few tests. The prediction is, here it is, that if a planet goes in front, you get the orientation right, the planet goes in front, the light changes by a fraction. And it has been like, if you look at a New York skyscraper, and all the blinds are up, and one person's bulls are blind down, this is the change in light, fractions of a tenth of a percent. This was the prediction. We looked at quite a big planet, and they showed me this, and I said, actually, can I see the data before it's been processed? And they said, this is the raw data, Matt. It's perfect. The telescope is so stable. The error bars are very small. This is what the transit curve that we saw from this very big, it's not an exoplanet, it's an exoplanet, but it's a very big puffy planet. It's just to try the technique. We moved to another gas giant, WASP 39b. What you can see here is that the transit depth changes with wavelength. So each one of those colors is a different wavelength. And those differences in transit allow us to take a spectrum of the exoplanet atmosphere as it goes past. Those minute changes, fractions of a percent in different colors, and we were able to detect carbon dioxide. On another planet, quite far away from here and rather big, again, it's a test, we were able to detect water vapor in the outer atmosphere. Nothing surprising about this. This is a big, puffy, like Jupiter thing, but it tells us this telescope will take spectra of exoplanets in the simple engineering test that we did. And in fact, I don't know what the results are, but this week we started looking at this TRAPPIST system. This is, again, the system I told you before. It's a red star. It's not like our sun. So the planets are much closer in, but it's quite nearby. It's only 40 light years from here. And it has 3 planets, at least, in the habitable zone. So this is the first target for James Webb, to see, can we see anything interesting in rocky planets in the habitable zone of this M star? We don't yet know whether that will happen, but those observations have started. And in fact, we have a lot of exoplanets out there. We now know, as we said, almost every star has an exoplanet. So there's a rich hunting ground for James Webb. But is it rich enough? So that leads me to the last part of this. James Webb not only is pointing us scientifically and engaging a large audience, it's actually beginning to point us what we might need to do next. You know, I said that we started the James Webb before the Hubble was launched. Well, we actually started thinking about what the next telescope should be before the Webb was launched. And now we know at least that these predictions that we did, a 6.5 meter telescope will be able to look at tens of different stars. There are very few yellow stars here. We really want to know, are there rocky planets going around a star like our sun? And there are not very many within the reach of the Webb. But if we want to go to the next level, it turns out it's a very sensitive function of diameter. If you just double the diameter and move to the optical rather than the infrared, we'll actually be able to get hundreds of planetary systems that we can take real spectrum of. And we now know how that's going to work because we've got it working on the James Webb. So the final part of this story is we're also being pointed what to do next. Because it turns out NASA, ESA, and the Canadian Space Agency have developed this technique of big telescopes in space that can be unfolded. And you can imagine taking the next step, something we colloquially call the Sagan Observatory. Taking the same technology, moving to the optical, twice the size. NASA's building some very, very big rockets. So is Elon Musk. all of which become available to us in the next decade. And it turns out we now have, as the famous said, we now have the technology. We also have the knowledge to do this. And that's where the next step is taken. So the James Webb has actually not only opened our eyes to a new scientific horizon, a new era, it not only has engaged a great population, it is also pointing us what our next mission needs to be, what the next generation needs to focus on for the next 10 to 15 to 20 years. It's changing the way we think about the universe, but the person who says this best isn't me, it's actually Carl Sagan himself.
We were hunters and foragers. The frontier was everywhere. We were bounded only by the earth and the ocean and the sky. The open road still softly calls. Our little terraqueous globe is the madhouse of those 100,000 millions of worlds. We who cannot even put our own planetary home in order, riven with rivalries and hatreds, are we to venture out into space? By the time we're ready to settle even the nearest other planetary systems, we will have changed. The simple passage of so many generations will have changed us. Necessity will have changed us. We're an adaptable species. It will not be we who reach Alpha Centauri and the other nearby stars. It will be a species very like us, but with more of our strengths and fewer of our weaknesses. More confident, far-seeing, capable, and prudent. For all our failings, despite our limitations and fallibilities, we humans are capable of greatness. What new wonders undreamt of in our time will we have wrought in another generation and another? How far will our nomadic species have wandered by the end of the next century and the next millennium? Our remote descendants, safely arrayed on many worlds through the solar system and beyond, will be unified by their common heritage, by their regard for their home planet, and by the knowledge that whatever other life may be, the only humans in all the universe come from Earth. They will gaze up and strain to find the blue dot in their skies. They will marvel at how vulnerable the repository of all our potential once was, how perilous our infancy, how humble our beginnings, how many rivers we had to cross before we found our way.
The fact that 20,000 people, some of the largest aerospace companies in the United States, in Europe, and in Canada, the fact agencies, were all able to work together on a single objective based simply on the idea this is a pure science mission gives me hope that we can cross that next river. That's what we can do when we actually have these kind of ideas. That's why I have hope that we can solve complex problems in the future. And the Webb is already showing us the way. Here is the first imaging of some of the exoplanets. They're not close, but it shows it works. But it leaves me in a very optimistic place. Having the privilege of having worked on this mission, I've seen what people can do when they work together based purely on an idea. Thank you.
Thank you, Matt. That was literally breathtaking. So let's take some questions from the room, and then we'll go to those people online. So who's first? Gentleman here. Oh, can you wait for the microphone, please, because the people online can't hear you without a microphone.
What is the detector gap?
I'm sorry?
The detector gap.
What do you mean by the detector gap?
On one of the slides. On one of the slides, it seemed to be an area where there was no data received.
Well, I mean, the detectors themselves are spatially positioned when we tend to mosaic. Some of the wavelengths don't completely, in some of the instruments, I'm not exactly sure which part of it. Sometimes we've only processed some of the data, not all of it. I don't know which gap you were looking at. Yeah, I mean, I'm happy to tell you after. You can show me what you were talking about afterwards.
Yeah, Daniela?
When you show the plot with the measurement of the Hubble constant, it seems like there was like a change, systematic change between WMAP and Planck. Can you comment?
I can't comment because I only read the paper. It is a fascinating, if you're on the observing side looking at the measurements today, you ask the team, which is represented by JWST, is that a systematic error? They say no. Because it turns out that if you look at the actual error bars, the measurements from originally COBE and then WMAP and now Planck are actually quite statistically consistent. It's just the trend is in the wrong direction.
The trend seems to be different.
Trend is different. And so it does appear that, I mean, the two components I put up there, I mean, nobody has found an error in either side's calculations, which is why this 5 sigma difference is now significant. Before, when it was 1 or 2, you guys haven't done this right, or you haven't done that right. Now, as JWST says, now I believe it's a crisis. There is something clearly missing in the calculation. And, whether it's early dark energy, or there's another neutrino, or there's another force, or something's wrong with our calculations of gravity because the dark energy calculation, we don't know. But it is now become interesting because something isn't right.
We've got a question online here, I think. Becky, is that right?
Jorge Aponte Gomez online asks, what can damage the telescope, and is there a chance that this can happen? Sorry if that's made you a little bit twitchy to damage your baby.
We had several meteor strikes on this telescope, and one of them was really bad. It actually bent the mirror, which worried us intensely. We did know that there would be a flux. Nobody quite knows what the fluximeter is out is at L2. We rely on different spacecraft. So we were worried that we'd got that calculation wrong. It turns out we hadn't, or at least the calculations are consistent, but we hadn't anticipated there was one component on the mirror which was far more susceptible to a direct hit than we had fully understood. So when we do those calculations and take out that it's a little bit of triangular aluminium, literally about this size, the meteor happened to hit that, and that bent the mirror. So meteors are probably the life-limiting factor of this mission, not because they'll damage the mirrors, but ultimately they'll perforate these 5 layers of sunshade, and there'll be enough sight lines eventually, statistically, to begin to warm the mirror up. The 5 layers are there because we were trying to reduce that statistical variance. It could have been 4, but we chose 5 to give it a longer lifetime with micrometeorite damage out there.
Another one online? Is there another one here? James? Yeah.
So we have a question from Chris, who asks, when you were asking for the extra 800 million funding, at various points throughout the talk, you mentioned that you didn't know whether a section of the telescope was going to work or whether the mirrors were going to work at the end of it. So what did you tell them about that? How honest were you? And what did they say when you did?
So when you do these big projects, there is a certain sophistication in the sense that they know this is near the edge of the impossible, to use a phrase that we use a lot. They want to know, have you done what testing you can do? Is it going to work? And we say yes, because that's what the models tell us, right? And what we have discovered, when it doesn't work, the whole point about this is that when these 10 things fell off, we had to go and tell them that we were going to get delayed. The only problem was there were no other people behind me when I walked into the room. I would look around there, they're all gone, And so, And so we had to go through the hearing, we had to change management, we had all of those things. And $800 million later, we got to where we were. So we spent $9.8 billion with US taxpayers' money on this. So it had better work. And we are thankful it did. And since that point, everybody loves it because it works, you know? I mean, the enormous thing is, if it works, we are forgiven a lot of sins.
Okay, let's take a couple more questions from the room. First here, and then so we don't delay, a second one there.
Just speaking of that $800 million figure, you mentioned, you know, SpaceX and Elon Musk in passing, and you've also mentioned going to have to justify that spend to the federal government. When you look at that 12-meter telescope and that vision that you closed your lecture with, how concerned are you about the imagination of the federal government in funding these programs and the sustainability of that when you're dealing with competing spending from private sector actors like Elon Musk?
Well, first of all, Elon Musk doesn't do anything unless somebody pays him to do it. There's no, you know, philanthropic side at the scale that we need, right? That's the first thing. The second is that it isn't just us that goes to ask for funding. That's the key point about this. If you can't have aerospace, before things go wrong, when you're actually starting a project, if the aerospace companies come with you and say, we think this is important for us, that makes it. You have to have a compelling science case. You have to be truthful. We have the National Academy to do it. We have aerospace that said, this technology we'd like to give. When I go to give a talk at Northrop Grumman, the first time I did this, you know, they said, will you come and talk to the team at Northrop Grumman? You know, and there was about 100 people. I said, okay, sure. I give a talk to 100 people, so what? I walk in, and there was about 500 people in the room. I go, all these people work at James Webb? No wonder it's so expensive. No, none of these people they came from the Air Force, they came from the airplane sector or the missile sector or this. Because we work in the open, they can go home at night and tell their families, this is what Northrop Grumman does. So that has a huge symbolic power. Now, don't get me wrong, they make money doing this. These are all cost-plus contracts. But the inspirational value of these, I didn't actually show one of the videos, the engineers queue up to work on these missions because A, they're exciting, and B, they can talk about them. When you work in the aerospace industry in the United States, 90% of the work you do is classified. And so that actually helps. And then when we say, okay, we have this plan, we want to maintain your core competencies, we want to further develop your technologies, other agencies might be interested. Okay, as long as you give the science case and you go in the room first, we'll be there behind you, Matt. So, you know, that's, but it is, you know, it's what people like me are paid to do. Yeah.
So I want to make a comment on that, and then we'll have a question here, so please pass the mic across. You can hear me, I think. So just to make a comment on this, a local comment, of course, that's exactly how the department here works as well. Right? You know, we have fantastic technical staff in the department, wonderful engineers and IT people, and we keep them because we give them really exciting, interesting things to do. This is the Thames Valley, they get paid more money elsewhere, but they stay here and work with us because it's exciting.
Exactly.
Let's take the next question.
Hi, actually my question is slightly related to the previous ones. It seems to me that the logistics of such a big project must be fascinating. What do you think is the key for the success of a project that takes so long, involves so many people, many of which with very, very different expertise, talking different languages, I mean scientific languages. What do you think is the key for such a big project?
I'm not sure there's a quick answer to that question. What I observe is what Roger just said. If people are excited by the idea, they will commit to it. The next problem is that you realize you reach a certain scale where no one person can keep the whole thing in their head. So you have to put in place a whole infrastructure called systems engineering, which is a very bureaucratic process for keeping each part talking to each other all the time. And then you actually need transparency. One of the wonderful things about the James Webb project is it operated what's called like a badgeless team. Now, in the United States, that means that when you walk into a room and you're trying to solve a problem, nobody's wearing a Northrop badge or a NASA badge or a Space Telescope badge or Aura badge. They're wearing a James Webb badge. And that turns out to be far more important than I had fully appreciated when I started. So the lesson I learned is transparency, communication, and vision. And if you can put those things together, and then a certain discipline. So you sit through hours in rooms like this, looking at detailed charts that have red, orange, and green, And you watch over the course of the years if the thousands of elements start turning green. In fact, I kept the last chart from System Engineer, which I have, which shows all green. And it's that bureaucratic process that once you go over roughly 100 people, you have to have in place. But if you do it, you get telescopes like the James Webb. So that's the payback.
We're going to take one more question online, and there's a gentleman here with a question. Oh, sorry, it was the gentleman in front, actually, but okay, we'll take that question first and then that one. You go for now.
Oh, me go for it. So Steve online asks, have the images of the galaxies at great distance and their improved resolution, as far back as 13.1 billion years, changed our understanding of the evolution of the universe immediately after the Big Bang?
Not yet, but some people think that the disks are forming too quickly compared to models. That's what that paper I showed. I haven't read it in detail. Again, I worry that people have got too used to thinking about high redshift galaxies seeing with the Hubble. So you're seeing ultraviolet light redshifted to what we can see. We've never seen high redshift galaxies in actual optical wavelengths because we see them in infrared. And that we don't know yet whether those models are right. The paper claims that disks are forming too quickly. But again, it literally only came out recently, so we need to have another look. So we'll wait and see. Something will change because it turns out this is turning out to be, wherever we look, we see galaxies, and so the data is beginning to be accumulated. We haven't got the calibrations quite right yet, and that's the other problem. The calibrations still need a little bit more work, and it really matters how well this data is calibrated for those kind of questions.
So here, and then the gentleman behind.
So Hubble has been working way beyond the design life. I just wondered what the limitation was in terms of the service life for James Webb, and also, do you wish you would have had a spare sun shield sort of stowed away on the spacecraft?
So, okay, that's this compound question. First of all, the original life limiting factor of James Webb was 5-year mission with another 5-year goal was the fuel. How much fuel? Because you're sitting out at a metastable point called L2 where we have to station keep. However, Ariane did such a good job positioning it. I mean, basically it's a slingshot. We didn't expect to see that deployment of the solar sail. That wasn't supposed to happen. What was supposed to happen, it got launched, it would work out where it was, it would adjust itself, fire a few jets, and off it would go, and then when it was in the right place, it would go. The fact it deployed the solar sail so quickly is because Ariane hit it perfectly. We now have 25 years of life for fuel as a result of that trajectory. That doesn't mean we're going to last 25 years. We have the sun shield and the instruments to worry about how long those last. And we don't know the answer to that question. But I would easily bet on 12 years. And if I was feeling really lucky, I might bet on 15. I don't know if I can go beyond that because we are moving instruments and all those kind of things. I don't quite know how the micrometeorite damage will go. And yes, the future telescope will actually have a shield around the mirror this time because the micrometeorites took us a bit by surprise. And glass mirrors are going to be a little more delicate than beryllium.
Okay.
On the back on the engineering side, you say that when you focused the telescope, you're talking in terms of nanometers. What is the mechanism? Have you got little electric motors, or have you got magnets, or what? How do you move something in terms of nanometers?
It's an amazing mechanism. It's actually on the website. And it's a leaf spring system, as they call, with motors and it's literally gears, and a motor and reducing gears and then bending some flexures. But it is a mechanical device. Mechanical engineers had a blast working on the James Webb. It's a quite remarkable design feat, because this thing has to work in a vacuum at minus 230 Kelvin. But so when the mirrors were in the launch state, they had to move an inch, right? Excuse my imperial units, had to move an inch before we got it. It took 2 weeks to move that because we had to move nanometers at a time. And somebody actually got some grass and left it in the control room and said, the mirrors are moving the same speed as this grass, which they were. And then somebody forgot to water the grass and they died, and we thought that was a bad karma.
I was going to wind up there, but that's not a good note to end on. Another question from the room, and then we should wind up.
Well, karma was good because everything worked.
Yeah, Gavin.
What about radiation damage on the detectors?
The detectors are pretty buried inside the instruments themselves. I mean, one of the problems with Webb is they are really buried inside, right? And remember, they're all running cryogenically, so they also have a lot of radiation shields around them as well, you know? And they've been hardened, right? We're less worried about that than we are perhaps about radiation damage of the electronics on the sun side. There's a warm side of the telescope, you know, that points towards the Earth, where all their avionics are, where the gyros are, where the reaction wheels that point the message. That was where I would worry first. We are seeing cosmic rays events, but that again, that's fairly predictable.
Okay, thank you very much, Matt. You have successfully conveyed the huge excitement of this project. Exciting times we live in. Let's thank Matt again.